I would only say that, I get invited to give talks all around the world, and most of the time I say no, but I could not resist this invitation, so here I am. It's a real pleasure to be with you. So the task that I was assigned with was to, I think, as I understood it, was to explore the possibility that memories could be erased in the way that they are in this film. You want me to move something? The way they are in this film, using this device called a Neuralyzer, which is right here. But what I thought I would do to set this up is to ask a more fundamental question, which is how is it that we're able to recognize this actor, Will Smith? I think everyone's familiar with Will. And so what does that mean? What does that mean that we recognize Will Smith? Well, it means that a memory has been formed in our brains. When we see an image of Will Smith, we have no problem recognizing him. And that's despite the fact, well, probably we've never met him. But also we've had a lot of experiences since the first Will Smith movie or the last Will Smith movie that we ever saw. And yet this is a very stable memory. So is this power of visual recognition, particularly visual recognition of faces, unique to human beings? It's certainly a skill that we depend on and rely on in our social interactions. Well, the answer to that question is no. It's a widespread phenomenon. It's shared by many mammalian species, and I wanted to show you a little movie clip for you film nuts.
Ever get the feeling you're being watched? If you're out for a stroll on the farm, you might be right. That's because sheep and their sweet, woolly-faced lambs have a secret. Like people, these farm animals have specialized neurons that focus on faces, and they remember those faces for years. Researchers think our brains process faces not as a collection of features, but as integrated wholes for which we extract the information from 2 or 3D representations. To find out if sheep can recognize faces in this way, researchers trained them to recognize photos of celebrities. The sheep had to choose between the celebrity and either a blank screen, an object, or an unknown person. All the sheep passed the test, scoring an average of 80%, showing that they can learn to recognize unfamiliar faces, even in 2D. But are the sheep memorizing the images, or do they recognize individuals? In a second test, sheep had to choose between a celebrity's face, shown at a different angle, and an unfamiliar person. Humans can do this, but our accuracy drops from around 90% to 76%. Turns out there was no pulling the wool over these ovine eyes. The sheep passed the test with a drop in performance similar to people. That means that sheep, like humans and other primates, seem to have advanced face recognition abilities, something to keep in mind the next time you come face to muzzle with one of these gazing grazers.
Wow, I love that. So I guess the moral of the story there is that we can learn about visual recognition memory by doing studies on animals, and a lot of studies have been done over the years, and we've learned a great deal about what happens when you learn to recognize a face, such as, maybe you're going to learn to recognize me or not, but I'm giving you a chance by showing up here. So I suppose the way we would break it down from a neuroscience point of view is to ask, well, how are these images represented in the brain, and where are they represented in the brain? And what I'm showing here is a cartoon of a human brain. Of course, the visual system starts with the eyes and the retinas, so images of faces are formed on the retinas. Then information is transferred into the rest of the brain through nerve impulses, and it's transferred ultimately to a part of the brain at the back called the primary visual cortex. It's in the occipital lobe at the back of the head. And then that information, there's sort of elementary processing or breaking down of the features of images that occurs in primary visual cortex. And then that information is then distributed to a bunch of higher order visual areas. And one of the sort of streams of information that comes out of primary visual cortex is called the ventral stream. It's the one shown at the bottom, is the visual areas that are concerned with recognizing the identity of objects. The dorsal stream is involved in recognizing motion and things like that. And in fact, there's an area of the human brain called area IT, the inferotemporal cortex, where if we were to actually stick a microelectrode in and record neurons, the activity of neurons there, what we would find is that there are neurons that will respond very selectively to specific faces. So it's sort of a clear representation of faces. There's a human clinical condition that's quite rare but very interesting called prosopagnosia, which is damage to that part of the brain, leading to an amnesia for faces. So how do these memories form and how do they last for a lifetime? This type of memory we call declarative memory. It's a memory for facts, events, places, faces. And the way to think about it is that information flows into the brain through the sensory systems, the eyes, for example. And they lay down a trace, and that's a trace that is laid down by modifying connections between neurons. And this is a stable physical change in the brain, and we're going to call this short-term memory. And the reason it's called short-term memory is that many of those memories, whereas they're robust, in the same sense that you remember what you had for breakfast this morning, despite you've had an entire day of other activities, they are easily forgotten. Short-term memories are easily forgotten. And that's a blessing, because most of the experiences that we have in life are not memorable, they're not going to help us survive, and they're probably better off forgotten. But of course, some memories are critical for survival, and so a subset of these memories are then consolidated into what we call long-term memory, which is a very stable form of memory. So it's really a transformation of memory in two important ways. One of the ways is where the information is stored in the brain. So when it's stored in still a short-term form, one that's easily forgotten, there's sort of a shared load between two different parts of the brain. A part that you may have heard of called the hippocampus, and the cerebral cortex, which is actually what I showed you in the last slide, which is just this surface of the brain, the structure that is on the surface of the brain, the cerebral cortex. As memories are consolidated, there is less and less of a role for the hippocampus, so that information is transferred entirely to the cortex. So one step of consolidation is just changing the location of where the information is stored. At a more molecular level, there are biological mechanisms that change the way information is stored as well. So initially, these memories are quite rapidly formed by modifying synaptic connections between neurons. And these modifications don't require anything fancy like new gene expression or protein synthesis. It can be what we call post-translational modification of proteins in the brain. That is, these are proteins that make synapses stronger or weaker, and they can be modified in ways that will represent information for a period of time, but not forever, but for a period of time. The memories that are saved or stored into long-term memory is an additional process that occurs that does require protein synthesis. So there's a dividing line in memory at the molecular level. Short-term memories do not require protein synthesis in the brain. Long-term memories do. So if we imagine what happened the first time that we saw a movie with Will Smith in it, we have this image of Will formed on our retinas. It makes its way through primary visual cortex. Finally, it comes down in here to area IT, the inferotemporal cortex, the temporal lobes. And there's communication between the inferotemporal cortex and the hippocampus. So the hippocampus is this structure that's shown. It's buried inside the temporal lobe, so you can't see it from the surface of the brain. But if you were to cut the brain in half, as shown in the left side here, that reveals the hippocampus. And in fact, in cross-section, it's got this appearance of a seahorse And so it's given the Greek name for seahorse, hippocampus. And so the hippocampus is a critical way station. So all these short-term memories pass through the hippocampus en route, and they reside in the hippocampus in coordination with the cortex, en route to finally consolidated storage in the cortex. Now, after memory consolidation occurs, there's this the memory consolidation occurs by this communication from hippocampus back to the cortex, and that occurs over time, over days. And a lot of the critical action in that communication is actually occurring during sleep. So we now understand that the communication from hippocampus to cortex is particularly important during phases of sleep that are called slow wave sleep. So slow wave sleep is critical for formation of consolidated long-term memories. Now, the reason we know so much about the hippocampus and why everybody's obsessed with studying hippocampus in the context of memory is a very famous clinical case. It was a patient that I've known for most of my life as patient HM. He was only known by his initials. And he died some years ago, and now his identity was revealed. That's Henry Molaison. Now, Henry had a normal childhood, but he developed severe epilepsy. And epilepsy often will originate with abnormal electrical activity in the temporal lobes, the temporal parts of the brain. And so for people with epilepsy that cannot be treated with drugs, often the next strategy to control the epilepsy is to go in and remove the diseased part of the brain. And that means removing part of the temporal lobe in the brain. This is a fairly common procedure. It's still done today. But in the case of Henry's, HM's epilepsy, it had spread so that both temporal lobes were affected. So both temporal lobes were giving rise to this abnormal electrical discharges. So the treatment to control this epilepsy was to go in and remove the temporal lobes in both sides of the brain. And that's what's shown on the bottom here is these are CAT scans of the brain of HM showing that the temporal lobes, tips of the temporal lobes have been removed, particularly the parts of the brain that contain the hippocampus. So the hippocampus is absent. So what happened to HM? Well,
What you did yesterday?
No, I don't.
How about this morning?
I don't even remember that.
Could you tell me what you had for lunch today?
I don't know, to tell you the truth.
so HM's completely unable to learn, from the moment of that surgery onward, he was completely unable to form any new long-term memories. So we had interrupted this circuit that's required for long-term memory formation. Now, in addition to the failure to be able to encode new memories, that's a type of amnesia that we call anterograde. It's from the moment of the surgery forward is an amnesia, inability to learn anything new. He could still recall distant memories. So he remembered John Kennedy, he remembered things from his childhood, things from his past. So those memories were intact, they didn't require the hippocampus. But when they studied him more carefully, they realized he had what was called a graded retrograde amnesia. So events that occurred proximal to the surgery, so in the weeks or months or even years just before the surgery, those memories were also disrupted. So there was a loss of memory of events that had occurred in the past. Now, this retrograde amnesia is a common consequence of any manipulation that disrupts hippocampal function, even temporarily. And the classic example is head trauma. So if you were bonked in the head after this film on the way home, you would very likely lose the memory of the film and your lecturer today. So memory for me would be lost, but you'd still remember Will Smith, okay? So you would lose some memories that were still in a vulnerable state. They could go back as long as weeks or even months. You could lose memories that far back before they've been fully consolidated in the cortex. So that's one way to disrupt hippocampal function. I couldn't resist. I found this paper when I was researching this topic. It's just published in a credible journal called Forgettable Sex, a case of transient global amnesia. A woman had, when she achieved orgasm, there was an ischemic event in her brain, temporarily impaired the hippocampal function, and woke up, said, who are you? who are you in my bed? Anyway. So erasing consolidated memories is hard, unlike what is in the movie. There are ways that it can be done. It requires some knowledge of the sort of molecular part, which I think I'm probably running out of time. But simply said, I said memory consolidation requires protein synthesis, and the way it goes is the genes create messenger RNA molecules. These are translated into proteins. And these proteins are required for stabilizing memory. That's why if we block protein synthesis, you lose memory. Now the proteins themselves have a temporary finite lifetime. They can be degraded. But one of the key features of this particular protein, which is called PKM zeta, is that it feeds back and keeps turning on the translation of the gene. So it's like flipping a switch that occurs at every synapse. And that's what maintains memories, even though all the molecules in our brain turn over our lifetime, over a matter of weeks. Most of the interesting proteins have turned over. Yet this can maintain memory. So is it possible? Yes. We can do manipulations experimentally that will impair the ability of this particular protein to feed back and maintain that switch in the on position. And once you flip the switch off, the proteins degrade, the memory's lost. And so, yes, it might be possible someday to come up with a quick and easy way to erase people's memory. That's it.
That's fantastic. Don't worry about the time. We're all good. We're all good. That was fascinating, and your slides were amazing. I think this is probably the best presentation we've had in 3 years. So thank you very much, Mark, for providing that with us. I was just going to open up the audience to the audience. Any questions? Any question about memory, your memory, or memory in general? This is probably your only chance to speak with one of the leading experts in the world. Okay, Larry, here's your chance.
Do you always lose short? Or maybe I should phrase it differently. Do we lose short-term memory throughout our lives?
Well,
So if I lose my glasses, is that short-term memory?
so there's another type of memory called working memory, which is the sort of memory we rely on to remember a phone number between looking it up and going to the phone. Certainly that becomes impaired with increasing age. Short-term memory is impaired with increasing age. And the reason is, frankly, is because all the neurons we were ever going to have, we had when we were about 20 years of age. So, unless anybody here is less than 20, there's one. For you, you have more neurons than your father, I promise you. So, it doesn't, I'm not justifying back talk, mind you, but anyway, so brain function will gracefully decline with age.
So a wife or a girlfriend's not going to be upset with you because you have short-term memory?
No. She shouldn't be, no.
Yes.
Mark, why is it that I sit regularly with the mentor, the department chairman at Northeastern that I taught under for 25 years, and when I go to visit him every Friday, he'll remember things in enormous detail. A bank robbery that took place in Clearfield, Pennsylvania in 1926. And I'll say, why did you think about that? He goes, well, I was there, I saw the whole thing. And yet, these things come alive every week when I come to see him. He doesn't think of them, that it doesn't occur to him. Why are these things lighting up and coming to the surface, that have been lying dormant?
Well, that's a good question. The way our memories work, it's believed, is that they are what's called content addressable. So, you know what it's like when you're trying to recall a memory? Like, I couldn't remember the name of the actor in Little Miss Sunshine, I still can't, but it'll come to me. But the way we do it is we start working around it, in our minds. and trying to fill in a piece. So essentially, the memories will become complete and very vivid once you've sort of triggered that whole ensemble, that whole collection of neurons to be firing at the same time, and then it brings the memory back. And for the, when I can't remember this actor's name, it's because I haven't provided enough clues for that ensemble of neurons to become active. And I'll probably remember when I walk home. And so in this case, I would assume it's because there's some association that he's forming that is just very vividly bringing back that memory in great detail. Now, on the other hand, it's also probably important to remember that every time you recall a memory, you are further strengthening it in a way, right? But it's also subject to corruption. And that's a process we now know is called reconsolidation. And in fact, psychologists have known about this for years, but when you recall a memory, you actually can put it back into a vulnerable state again. So if we recall a memory and then give a protein synthesis inhibitor, which remember blocks consolidation, it can impair the rewriting of that memory into long-term memory. And that's a strategy, conceptually anyway, to treat things like post-traumatic stress disorder.
Question here.
Hi, thanks so much for being here tonight. 2 quick questions, well maybe not quick, but the first is the role of electricity. You use the metaphor of circuitry, so the role of electricity relative to things like protein, physiological chemistry, structural, in memory. So that's just sort of just a general question because that didn't come up. And the second is just a question on sort of the state of the art. I heard a speech a few years ago by the person who ran the National Institutes of Health, and they said that basically 90% of what we know about the human brain we've learned in the last decade or something along those orders of magnitude. Where do you see, sort of given your career arc, where are we as far as what we know today, and what's the rate of change for what we'll know when he's my age?
Yeah, those are good questions, and if I have to engage my memory long enough to remember both questions. But so the first question about electrical activity versus changes in proteins. So the brain's made up of many neurons, billions of neurons, and these neurons communicate with one another through essentially analogous to wires. So they're called axons or neurites that connect one neuron to another. And so for information to travel across a distance, there is an electrical impulse. So for example, if I stepped on a tack, it's going to cause neurons down there to fire electrical impulses. They're going to come all the way up the nerves of my leg, into my spinal cord, all the way up to the base of my head, to the first synaptic relay. So these are nerve impulses. They are electrical. We can record them with the way you would record any electrical signal. And they're really specialized, particularly for this transmission across the distance. The way, the impact of those signals on that receiving neuron requires participation of proteins. I mean, even those electrical signals require participation of proteins. And it is those proteins can be modified, and that will modify the sort of strength of that signal activating the target neuron. And it's those sort of modifications that we are sure serve memory, which is the fine-tuning of now trillions, literally trillions of synapses in the brain when we have experiences. So in biology, electricity and proteins are inseparable, really inseparable. Now, in terms of the pace of neuroscience research, oh my God. So I've been doing this for 40 years, and I agree. If Francis Collins said that, I agree with him, that in the last 10 years, it's been an incredible explosion of knowledge. And I think really it traces back to the Human Genome Project, honestly. Once they cracked the genome, and not just of humans, but also of mice and other species that we study, it opened up approaches to interrogate and manipulate neurons in a way that I could never have imagined 40 years ago. And I think the problem that we have now is a data explosion. So it's just overwhelming, the amount of information that we're learning. some of it seems very fancy and sophisticated, but ultimately is trivial. So, hate to say it, and so it's pretty hard to filter out, to get the signal and the noise sometimes. So, at a conceptual level, I'm not sure we've advanced that far, to be honest. But that will come. That will come. I pray.
One last question, Mark.
Yeah.
You seem to have been talking about the creation of memory. I'm particularly interested in the reverse that occurs perhaps in Alzheimer's, and particularly white matter. And I wondered whether you could briefly speak to how white matter interrupts the consolidation of memory.
Sure. So, we're all familiar with what nerves are. So these are collections of these so-called axons that allow neurons to communicate across distances. So these are the nerves in our body. Inside the central nervous system, we still have collections of these axons, but that's called white matter. So white matters are just bundles of hundreds of thousands of these axons that are absolutely critical for one part of the brain to communicate with another part of the brain. Now what happens there are a number of diseases that can affect white matter, for example, multiple sclerosis. And of course, every one of those axons in the white matter is connected to a neuron. There's a host neuron. Now what happens in Alzheimer's disease, unfortunately, is that the loss of neurons, that is a natural consequence of aging, is vastly accelerated. And so you can lose a lot of neurons that without a catastrophic effect, surprisingly. And that's why, unfortunately, in the case of Alzheimer's disease, it's often diagnosed quite late. So there's quite a large neuronal loss by the time you actually have complained that there's an impairment in cognition and you're tested. So that's one of the challenges that we have in terms of treating Alzheimer's disease, is that when it is detected or diagnosed, often the damage is sufficiently severe that it's impossible certainly impossible to reverse. You're never going to grow new neurons. You can mitigate the ongoing effects a little bit. So that's the sad truth about age is, as I said, we lose neurons as we get older, and some functions depend on large numbers of neurons, like cognition, and that's good because we can lose a lot and not see much of an effect. Other functions depend on a very small number of neurons, and then we see the effects much earlier. So an example of that would be Parkinson's disease, where there's a small collection of neurons in a part of the brain called substantia nigra, and they really number in the tens of thousands, I think. And so over the course of a lifespan, you eventually lose enough that you will acquire the symptoms of Parkinson's disease. And so if we all live long enough, we will all have Parkinson's disease.
Well, thank you so much, Mark. We could go on forever here, and maybe we will have you back. We would love to have you back in the summer, and maybe skip the movie and just do more presentation, because it's amazingly, interesting and universal in appeal. I mean, we all deal with this stuff. So again, thanks so much for joining us, and we'll be on with the movie. Yes, we still have a movie. We'll be on with the movie, and next month we have another